Hello and welcome back to Introduction to Computer Architecture. Hopefully the motivational video you watched previously kind of inspired you to keep watching. And we're going to start our lesson, or I guess the course itself, with talking about how computers represent information. You might have heard, on TV or in pop culture that computers are in fact just ones and zeros. They represent information entirely in ones and zeros. And hopefully by the end of this lesson and the next lesson, you'll be able to understand that any sort of information can be represented with a sequence of ones and zeros. Now let's move on to, or let's begin with, how do humans represent numbers? We think of numbers in base 10. So for example, the number 2115 can be represented with a 5 in the ones place, a 1 in the tens place, a 1 in the hundreds place, and a 1 in the thousands place. Now you notice that all the places are actually just powers of 10. So 1 is 10 to the 0, 10 is 10 to the 1, 100 is 10 to the 2, 1000 is 10 to the 3, and so on and so forth. We can go for infinitely large numbers. And with this representation, we can now express the number 2115 as a sum of the powers of 10. So it's actually 2 times 1000 plus 1 times 100 plus 1 times 10 plus 5 times 1. Why do humans represent numbers in base 10? Well, because it's convenient for us. If you look down at your hands right now, you'll notice you have 10 fingers. When you learn to count, you learn to count up to 10. And so we're really good at doing numbers in our heads that are base 10. We're just good at that. So it's convenient for us to represent numbers that way. But it's not convenient for computers to represent numbers this way. Computers represent numbers in base 2. What base 2 means is that instead of having a tens place and a ones place, or a ones place and a tens place, we're going to have a place of 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, so on and so forth. So the bases are in fact 1, 2, 4, 8, 16, 32, 64, so on and so forth. So how do we represent the 14 in base 2? Now you remember that I expressed the base 10 number as a sum of, as a linear combination of the bases. So here we're going to do the same thing. Basically what we want to do is we want to find an A, B, C, and D in this equation. So, some number of 8s, some number of 4s, some number of 2s, and some number of 1s will eventually give us the number 14. But how many? And you'll notice this is pretty confusing. We have 4 variables in one equation, and that's not really possible to solve. However, there's something that makes this equation easy with the fact that it's base 2. Now let's go back to human numbers. In human numbers, you know that the maximum you can go in any of the places is 9, right? I can't have, 2, 1, 1, 10, for example, and then say that I have a 10 in the ones place, right? This is incorrect. The maximum I can have is 9, because otherwise all I do is I move over to the next power of 10. Same thing with base 2. Now in base 2, what are all the possibilities of our numbers? We can either have 1s or 0s. And why exactly computers are good at doing things with 1s and 0s we'll learn in lecture 4. However, right now, all you have to think about is the maximum we can have for A, B, C, and D is 1, and the minimum we can have is 0. So that makes this equation a lot easier. Technically, we could just try out all of the possible ways. There's only 4 choose 2 ways to do it, but we're not really going to get into that. There is an algorithm for converting a decimal number to a binary number, but I'm not really going to get into it because I don't think it's very relevant to what I'm trying to teach you. This is more to teach you how computers represent information rather than the algorithm for conversion. So I'm just going to give this one to you. 14 is going to be 8 plus 4 plus 2, meaning that there is a 1 in the 8th place, a 1 in the 4th place, so 8, 4, a 1 in the 2th place, And then we also have a 0 times 1, as we did before. So I'm just going to rewrite this equation just so it looks like the one in the previous lecture. Just going to rewrite it so it looks like this. So 14 is going to be equal to 1 times 8 plus 1 times 4 plus 1 times 2 plus 0 times 1. And so we have the values for a, b, c, and d, and our binary representation of the number is 1, 1, 1, 0. The way that we denote bases of numbers is we put them in parentheses like this, and then put the base at the bottom. So this is base 2, and 14 is in base 10, and these are equal. To solidify your understanding of this, let's do some more examples. Here we have the number 10, and I've already written out the bases for you so that you don't forget. So again, we have 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3. Now, I want you to pause the video, and I want you to try and figure out what the binary representation of 10 is. So remember, you want to know if there's a 1 or a 0 in the 8's place, a 1 or a 0 in the 4's place, a 1 or a 0 in the 2's place, and a 1 or a 0 in the 1's place. So pause the video right now and take your time, and then we'll come back to it after you're done. Now that you're back, let's do this. So 10, it's going to be a 1 in the 8's place, a 0 in the 4th place, and a 1 in the 2's place, and a 0 in the 1's place. So the 10 is 1, 0, 1, 0. 8 plus 2. Okay, let's do another example for the number 6. I'm not gonna give you any guidance this time. I just want you to give me the binary representation. Pause the video now, and I'll come back to you. Now that we're back, 6 is represented as 0, 1, 1, 0. What that means is it's 0 times 8 plus 1 times 4 plus 1 times 2 plus 0 times 1, which is 6. Okay, so that's going to do it for this video. In the next video, we're going to talk about how these binary numbers can actually represent more than just decimal numbers and all types of things.